Hello, everyone. My name is Mohammed Rasheed, and I am an undergraduate researcher at Kansas State University in the Department of Mechanical and Nuclear Engineering. My research advisor is Professor Gurpreet Singh, and I'm here to present an assessment of polymer-derived quaternary CMCs. Now, to start with an outline, we will begin with a background and motivation, followed by a fabrication process. Then we will move on to characterization, testing, and results. And then finally, end with summary and future. So CMCs, or ceramic matrix composites, are promising materials for extreme environment applications. This is mainly due to their low density, high damage tolerance, and high temperature capabilities. And these CMCs are capable of meeting all of these requirements in a lightweight structural form. Previous research has focused on the use of traditional ceramics and ceramic monoliths, which have excellent oxidation resistance, but are unfortunately too brittle and too difficult to machine. So the CMC route provides an easy fabrication avenue for the application of these high temperature resistant ceramics. And carbon fiber reinforcement is commonly used in CMCs to prevent matrix crack propagation and improve their thermal shock and impact resistance. Carbon fibers also retain their mechanical properties at low to moderate temperatures and have a lower cost compared to fine ceramic fibers. And carbon fibers themselves also have applications in batteries, sensors, optoelectronics, and solar cells. So ceramic matrix composites, at least within the realm of this experiment, consisted of, like I mentioned, a carbon fiber reinforcement, similar to this image shown, as well as a ceramic matrix. And so some examples of some matrices are silicon carbide, aluminum oxide, and so on. And this is what a traditional ceramic matrix composite would look like. So you would have some fibers, maybe some sort of coating, and then of course the high strength ceramic matrix. So the motivation of the study is to assess the applicability of quaternary PDC CMCs in harsh conditions. The quaternary PDCs, specifically of SiXCN, exhibit exceptional structure and chemical stability at elevated temperatures. Previous research has shown that these materials remain amorphous at up to 1500 degrees C, have excellent creep resistance, and are stable to approximately 2000 degrees C. Of course, quaternary ceramics are not the only type of ceramics that exists. There are binary ceramics, which contain two components. Some examples include silicon carbide and hafnium carbide. There are ternary ceramics, which contain three components. Some examples include SiCN and SiOC. And of course, the main focus of this experiment is for quaternary ceramics, which include four components. So like I mentioned, SiXCN, where the X can represent boron, hafnium, or aluminum. And of course, something like SiCNO. And this has many applications. One of the more high demand applications are the aerospace industry. So it can be applied in something like a rocket nozzle or a nozzle extension. So the fabrication process first starts out with producing the polymer precursor liquid solution. And this took three routes. All routes begin with polysilazane, which includes the corresponding chemical formula. And three different precursors were made, one which will eventually turn into SiCN ceramic, one which will turn into SiBCN ceramic, and one which will turn into SiHFCN ceramic. So for the SiCN ceramic path, we took polysilazane and isopropanol in a 2-to-1 ratio. The main reason for using isopropanol in this case is to be used as a solvent, which will dilute the precursor and ensure optimal viscosity when coating carbon fibers. Furthermore, trimethyl borate was used to produce SiBCN, pre-ceramic liquid polymer. And finally, for SiHFCN, pre-ceramic polymer, polysilazane, isopropanol, and hafnium isopropoxide isopropanol were mixed in the following ratio to achieve the ideal pre-ceramic liquid. And so the fabrication process is as followed. The CMCs were fabricated using polymer infiltration, or PIP process, which is a well-known process for producing CMCs. And so it starts out with taking the liquid polymer solution, whether that be for SiCN, SiBCN, or SiHFCN. And in an argon atmospheric glove box, the carbon fibers were coated using a pipette. So this object here would represent the carbon fiber that is being coated. These were cross-linked in that same argon atmosphere at 180 degrees Celsius. And then in a tube furnace of nitrogen atmosphere, the samples were pyrolyzed to achieve the final ceramic state of the CMCs. Samples were coated with 3 drops, or approximately 60 microliters per each sample. And here are the fabricated CMCs images. So fiber bundles up here are shown. These were used for mechanical testing in the form of tensile testing. As you can see, here's the progression between neat or uncoated, cross-linked, and pyrolyzed. And then these discs were used for oxidation testing. So similarly, we have neat or uncoated, cross-linked, and then the final pyrolyzed mini composite mini CMC. Now, before testing, some SEM images were taken, mainly to verify the coating. And the SEM images revealed the fiber morphology for each case. And we started out with uncoated or neat carbon fiber. These fibers had an average fiber diameter ranging from 6 to 7 micrometers. Then some images of SiC uncoated fibers were taken, and the fiber radius did increase to a range of 7 to 8 micrometers on average. SiBCN samples similarly received an average fiber diameter of 9 to 12 micrometers, and SiHFC uncoated samples obtained an average fiber diameter of 7 to 8 micrometers. So as I mentioned, this increase in diameter verifies that the fibers were in fact coated. One special note to bring to your attention is that for the SiHFCN sample, you can see that there's some excess ceramic coating on the sides, which is not present in something like the SiBCN sample, for example, which had a more smooth coating. And this is mainly contributed to the fact that it is likely that an excess amount of pre-ceramic polymer was infiltrated into the sample. Next, moving on to the characterization. So in this experiment, there were many types of characterization techniques that were applied, but the two that I would like to focus on are the FTIR and XPS. So the FTIR shows the characteristic absorption bands of the polymer to ceramic conversions. So as shown, you can see the bonds that are present within the samples, both at the cross-linked and pyrolyzed stage. And then the XPS suggests the presence of various elements within the sample. And in this chart of elemental composition of XPS was achieved. So the values shown are quite expected for each type of sample. So silicon, carbon, nitrogen, and oxygen were present in the expected amount for each type of sample. SiCN, CMC, SiBCN, CMC, and SiHFCMC. And then, of course, for the SiBCN sample, a significant amount of boron was present. And for the SiHFCN sample, a significant amount of hafnium was present. And mechanical testing is as follows. So for mechanical testing, a Shimadzu universal testing machine was used to conduct tensile tests, and this was done at room temperature. So this is the device that was used. And before loading, samples were mounted onto a cardboard mount, and this is following ASTM C1557 guidelines. And this was mainly due to produce a better grip onto the tensile grippers. So this is a more close-up image, which shows the cardboard mounts being secured onto the tensile grips. And then, of course, before testing, these two ends were cut off to ensure that all of the loading was properly placed on the sample itself. And this is an after image of all of the samples. So for mechanical testing data, we also went ahead and tested some uncoated carbon fiber for the purpose of comparison. And as you can see, the results were quite consistent. The uncoated carbon fibers reached an average ultimate tensile strength of 2.38 gigapascals and an average Young's modulus of 75.1 gigapascals. Now for the CMCs, the results were also quite consistent throughout each sample. However, the results are as follows. So the average ultimate tensile strength was, for SICN, was 0.35 gigapascals, and the average Young's modulus was 45.3 gigapascals. For SIBCN, the average ultimate tensile strength was 0.1 gigapascal, and the average Young's modulus was 27.6 gigapascals. And for SIHFCN, the average ultimate tensile strength was 0.84 gigapascals, and the average Young's modulus was 60.9 gigapascals. So as you may have noticed, these values are much lower than the uncoated carbon fiber counterparts. However, this type of effect is expected, as during the fabrication process, the CMC has some weakened effects in its mechanical abilities. So now moving on to the oxidation testing. Oxidation tests were done in a Centrotech box furnace, and they were conducted in standard air and were heated at a rate of 5 degrees Celsius per minute. They were tested at 800, 1000, 1200, and 1500 degrees Celsius. So this is an image of how the samples would be placed into the box furnace. And the results are as follows. So the results show that the CMC samples survived the high oxidation environments, whereas the uncoated carbon fiber itself didn't actually survive any of the 4 oxidation tests. However, even though these CMC samples did survive, some significant disintegration, deformation, and changes in weight were shown at high temperatures. So as you can see visually, the CMCs look very much different from when they began at all temperatures. And the following rate retention percentages are shown in this table. So at 1500 degrees Celsius, SICN carbon fiber CMC had an 18% weight retention. SIBCN sample had a weight retention of 30%, and SIHFCN had a weight retention of 19%. Some SEM images were also taken, and these were mainly done to evaluate the oxidation behavior of the CMCs after heating. So in the SICN case, as you can see, some significant fiber dispersion is shown after 1000 degrees Celsius. For the SIBCN sample, after 1200 degrees Celsius, some significant deformations were shown, and a sort of kind of melting is shown, especially in the 1500 degrees Celsius. But comparatively to the other two, the SIHFCN sample had minimal damages present. As you can see, the matrix structure of the fibers survived and are visible at 1500 degrees C. So to conclude, quaternary ceramics were introduced as a matrix material for ceramic matrix composites using the PIP method. The mechanical test data indicates the viability of CMCs in structural applications. Oxidation test data indicates the viability and potential of CMCs in thermally harsh conditions. And of course, future work includes making variations in cross-linking and pyrolysis conditions and seeing the effect of the previously mentioned tests on those. The optimization of coating for purposes of creating a smooth coating on all the fibers and avoiding something like what happened to the SIHFCN sample, and the application of different reinforcements. Thank you so much for your time.